Katya. Thanks to Katya for the invitation to speak at this seminar. So this seminar is something that I've attended quite frequently over the past 2 years. And so I'm very happy to receive this opportunity to contribute back to the seminar. So today I'll be talking about the C-infinity isomorphism property for a class of singularly weighted X-ray transforms. And this work is one of several works, I guess one of in a series of works investigating the behavior of X-ray transforms, specifically their normal operators, particularly the mapping properties near the boundary. And so this is something that my postdoc mentor, Francois Monard, has been working quite a lot on. This particular work is joint work with Francois and Rohit Mishra, who was a postdoc at UCSC a few years ago. Okay, so to introduce the setting, I'll spend the first 2 or 3 slides going over the X-ray transform, which many people in this audience probably have a pretty good idea of, but I'll introduce it to just set the setting and conventions that I'll be working with. So the setting here is we have a Riemannian manifold with boundary, and for all practical purposes, you can think of this just as the literal Euclidean disk, and with a Riemannian metric being just the Euclidean metric. So so we could think about this very generally, but for all practical purposes, we'll just think of this as a very simple Euclidean disk. So given this Riemannian manifold with boundary, we can define the X-ray transform, and this is an operator which takes a function on our manifold, given I guess this function and a geodesic, say unit speed in the manifold, the X-ray transform just integrates the function along the geodesic. And so a classical problem would be to ask what are the properties of this X-ray transform? What are the mapping properties? If we know the X-ray transform, how do we get the function back, etc. So if we work with a manifold that is non-trapping and has convex boundary, then the space of geodesics, we can actually identify this more or less in a either 2-to-1 or 1-to-1 manner, depending on how you look at it, by the inward pointing sphere bundle. And so this is the partial plus SM. And so this will be a bundle. So you can think of this as saying that this you can consider a sphere bundle over the manifold with boundary, and this itself will be a manifold with boundary, and you can consider basically part of its own boundary. So here the inward pointing boundary consists of all vectors where the base point is on the boundary and the vector is inward pointing. In other words, you can describe it as a condition here where this function mu is the inner product in the metric sense of your vector with an inward pointing normal. And so we want this mu to be non-negative. And so given any such inward pointing vector, we can basically consider a geodesic which starts with that initial velocity vector, and that gives you an identification of geodesics on M with the inward pointing sphere bundle. And so as a concrete example, if we are considering M is the Euclidean disk, then the inward pointing sphere bundle can be identified with the manifold S1 cross -π/2 to π/2. The first vector S1, we can use the coordinate beta on it, and that basically represents the base point on the boundary. And the second coordinate we can call alpha, which represents the angle that a vector forms with the inward pointing normal. So in this case, I guess we are measuring alpha counterclockwise with respect to the inward pointing normal. And so we can give these coordinates beta alpha on the inward pointing sphere bundle, and we call these the fan beam coordinates. So in general, the X-ray transform, we can initially define it on, for example, continuous functions on M, but it actually extends boundarily as a map from L2 of M with the volume induced by the metric to L2 of the sphere bundle of the inward pointing sphere bundle, And with this particular measure, so this will be mu times d sigma squared. Mu, again, is the inner product of your vector with the inward pointing normal. And this d sigma squared is the so-called Sasaki volume form. And for practical purposes, again, in fan beam coordinates, you can think of this d sigma squared as just d beta d alpha. So this particular measure, it has some nice properties when you consider the adjoint of it, of the X-ray transform. And in fact, if we were to, in the case of the unit disk, if we were to parameterize the geodesics not by the fan beam coordinates, but rather to viewing them as lines in R2 via the coordinates s and omega. So s would be a real number and omega would be a element of S1 via the identification, that the equation of the line is given by s equals x out of omega. Then this measure mu d sigma squared, maybe equals is actually too strong of a statement, but it's certainly going to be proportional to ds d omega. So with that in mind, if we view the X-ray transform as mapping boundedly in this sense, then we could consider its formally its Hilbert adjoint, and this gives us a formal adjoint to the X-ray transform. And in fact, this is not anything too abstract. This is something that you can explicitly describe as the so-called back projection operator. So what this operator will do is that it will take a function on the inward pointing sphere bundle, which we identify with a space of geodesics, and it gives the outer function on the manifold itself, which essentially integrates out along all directions in the sphere bundle. So formally, you can write this as I0 sharp g of x is the integral over the fiber of the sphere bundle at x of g, composed with the so-called footprint map of all the unit vectors in the sphere bundle at x. So this footprint map is the map that takes a unit vector in the sphere bundle and gives you back the initial velocity along the geodesic, which passes through x with velocity v. But you can think, under the identification of geodesics with the elements of the inward pointing sphere bundle, you can think of this as just saying you're integrating your function on the geodesics over all geodesics passing through a point. Okay, and so in the classical case of, let's say, M is Euclidean space, then this is the well-known back projection operator that most of you are familiar with. And so the main object of study in this work, or the series of works, will be to consider the normal operator, which you get by composing the back projection operator, in other words, the adjoint of the X-ray transform, with the X-ray transform itself. And for our purposes, it suffices to actually, or it is actually necessary, to consider weighted versions of this normal operator. So we will pre-compose, before composing the adjoint of the X-ray transform with itself, we will also put in these weights in between. And these weights we can allow to be singular in the sense of that they might blow up near the boundary. So, so the main object here then is the so-called weighted normal operator, possibly with singular weights. And so we want to ask, what are some mapping properties of such operators? So, for example, in the Euclidean space, which isn't really part of what we're considering, since this is not really a manifold with boundary, but on Euclidean space, this is something that's very well understood, and it's very well understood that the normal operator is actually a Fourier multiplier. In fact, the Fourier multiplier is a constant, a dimensional constant, divided by the modulus of the Fourier variable. And the fact that it's a Fourier multiplier means that we can read off a lot of properties about a lot of mapping properties of this operator. So, for example, it takes a C infinity into C infinity, which actually I guess you can also see the other ways as well. But the point of having this Fourier formula is that you can then invert the normal operator, at least where the output has sufficient decay, by using the Fourier transform. So it seems that this operator will have a lot of nice properties. However, the Fourier equation actually only tells you nice properties about the regularity of the functions involved in the interior. As you move closer to I guess infinity in Rn, which you can view as the boundary of Rn in a pseudo maxification, the behavior breaks down a little bit, since here the Fourier multiplier for low c blows up, and kind of the heuristic in the Fourier transform is that low frequencies correspond to behavior at spatial infinity. So even in the case of m equals Rn, we already see that the normal operator can have some interesting behavior at infinity. And in general, if we want to consider a manifold with boundary, this is suggesting that the behavior near the boundary might be of interest and is certainly not trivial. So so for manifolds with boundary, the behavior of the normal operator might be more complicated at the boundary. And part of how we should think of this is for me, I was definitely very used to thinking of the normal operator as this elliptic pseudo-differential operator, and therefore it has very nice properties in the interior. Especially in terms of smooth, mapping smooth functions. However, for manifolds with boundary, if we view our manifold's boundary as a closed subset of some extension, so some extension m tilde, which is a manifold without boundary, then if we want to consider our operator, which we initially called I0 sharp W2, I0 W1, what this operator actually is this, but also with precomposed with the extension by zero map, and then postcomposed with the restriction of functions, restriction of functions from m tilde to m. And what that means is in this multiplication by the extension by zero, well, that makes things singular, or it definitely could. And so this operator, even if on manifolds without boundary, the normal operator seems like a very nice object. On manifolds with boundary, a priori, it's not clear what the mapping properties are. It's not even clear whether it takes a smooth function on the boundary into a smooth function on the boundary. So this motivates the main problem that we're studying, which is the following: that so implicit here is we have some manifold with boundary, and we want to ask, can we find weights? And if we can, which weights can we find such that when we do this singularly weighted normal operator, we get an isomorphism of C infinity. And just to emphasize that we are considering boundary behavior here, I want to point out that n I'm viewing as a manifold with including its boundary, and thus this notation C infinity of m means the space of smooth functions whose derivatives are continuous up to the boundary. And so the requirement of analyzing things up to the boundary is what makes this a tougher problem to look at. And such questions are quite important in for other problems. So, for example, there is this line of work by Francois and Richard Nicol and Gabriel Paternain, which look at various statistical recovery algorithms. And what's an important aspect of studying such algorithms is to obtain theoretical guarantees for consistency and uncertainty quantifications. And in order to obtain such theoretical guarantees, it turns out that you need to be able to say for certain that the normal operator, or some weighted version of it, maps bijectively between a set of spaces. And so it's not just enough to say that it maps in into some broad space of spaces. You need some sharp mapping properties to be able to make some basically invertibility statements. In addition, in studying the problem of an isomorphism, it's very likely, and it turns out to be the case, that we will end up with stability estimates. And we can, and so one way to derive an isomorphism for, C infinity, C infinity is to basically derive two-sided stability estimates on the operator, on our normal operator. And so, of course, stability estimates for the normal operator are of independent interest. And so, for example, from the work of Stefanov and Ullmann in 2004, we see that we can control the, so if we know the normal operator applied to some function, we can recover the L2 norm of the function, or we can control it by the H1 norm of the normal operator applied to F, as long as you're measuring this with respect to H1 of some extension M tilde. And so somehow there is a bit of a awkwardness here where you need an extension to phrase this problem, and it would be ideal to see if we can try to phrase this, obtain stability estimates without reference to an extension. So as I alluded to, this is this is a non-trivial problem to study, and in fact, if your initial intuition is that, oh, well, the normal operator is a very nice operator, well, because we're working with manifolds with boundary and we're studying the behavior up to the boundary, the behavior might not be as nice as you initially expect. And so some condition on the pair of weights that we want to look at, some condition on them is definitely necessary. As an example, suppose the weights that we chose were identically 1, i.e. we were considering just the straight up unweighted normal operator. So such a normal operator is well known to be an elliptic pseudo-differential operator in the interior, but it can have more complicated behavior at the boundary. And an explicit example of this is applying this normal operator to the function 1 on N. So the constant function 1, which is certainly continuous up to the boundary, smooth up to the boundary, in fact. And applying the normal operator to the constant function 1 gives us the back projection of the function tau being the length of the geodesic. And you can, in fact, compute explicitly in the case of M being the Euclidean disk, what this function ends up being. So essentially, this is a classical geometry problem where in a disk, you take a point on the disk and you're basically averaging the lengths of all the chords that pass through that point. And that number turns out to be given by an elliptic integral. And the main property of this elliptic integral is that its derivative is not bounded as you approach, as the input approaches 1. In other words, as our argument here approaches a boundary. And because the derivative is not bounded as you approach the boundary, that means that our output here, it does turn out to be a continuous function, but it is not smooth. In fact, it does not admit a continuous derivative up to the boundary. So even in this, very simple case, ideal case of like, oh, this, looks very simple, and we are on, for example, Euclidean disk where you can just explicitly do the calculation. It turns out that the normal operator, just the naive normal operator, it does not map C infinity into C infinity. In fact, it takes the constant function 1 to a function that is not smooth up to the boundary. A bit more work shows that, in fact, you can break up this output into a component that is smooth and a component that has a d log d term out in front, where d is the boundary defining function for the unit for our disk. And so, for example, you can take d to be 1 minus the radius squared. So again, it is continuous up to the boundary, and somehow the non-smoothness comes from this d log d term. So if we want to study when our normal operators are isomorphisms, well, first let's mention when when we know that our choice of weights will give us a normal logger which at least maps the infinity into itself. In other words, we need to already first account for forward mapping properties. So this is already a non-trivial task, as we saw in the last slide. And so it's worth mentioning some results about forward mapping properties. So in all of the results below, we'll take our manifold to be non-trapping with convex boundary so that we can, this gives us a lot of nice assumptions, but in particular, we can identify the space of geodesics with the inward pointing sphere bundle. So one of the seminal works in this line of business is a work by Pestov and Ullmann, where they constructed this space called C alpha infinity. And this consists of functions on the the inward pointing sphere bundle, so given a function on the inward pointing sphere bundle, you can try to extend it to a function on the entire sphere bundle. So, or the sphere bundle at the boundary, let's say, by extending via the scattering relation. So in other words, given an inward pointing vector, you can basically start the geodesic with that vector, see where it goes, and look at where it exits. And the exiting vector there will be an outward pointing vector. And the relationship between those two is called the scattering relation. And so given a function on the inward pointing sphere bundle, you could try to extend it to a function on all of partial SM by extending it, by defining it on the outward pointing part via the scattering relation. And doing so, in general, may give you a non-smooth function, right? So you might have a bit of a discontinuity or mismatch of inward and outward data. However, the space that they constructed here, the C alpha infinity, consists of functions which are smooth on the inward pointing bundle, but remain smooth when extended by the scattering relation. And the main a main upshot of considering such a space is a property that the back projection operator will in fact map this C alpha infinity into C infinity. This is notable, right? Because, for example, not all functions satisfy this. For example, the length of the geodesics, the tau function that we considered in the last slide, that does not satisfy this property. So this already tells us quite a lot about, well, this gives, I guess, a sufficient condition for a function on the sphere bundle side to be mapped into a smooth function. Furthermore, they showed not only this mapping into C infinity, but they showed that this is a surjection if n is simple. And so simple manifolds are a class of manifolds that is often studied here that has slightly more restrictions than just convex and non-trapping. Yeah, so in particular then, for our purposes, this means the following, that if we can choose our weights with a property that, let's say W2, I0, W1, if we can show that for a appropriate choice of weights, that it maps C infinity into this C alpha infinity space, then necessarily when you compose it by the back projection, you end up back in C infinity. So this gives a possible sufficient condition to at least have a forward mapping property. So in one of the works by Francois Richard-Nicol and Gabriel Patterning, they showed that we can consider the weights d to the gamma and tau to the 2 gamma plus 1, where d is a boundary defining function of our boundary, and tau is the length of the geodesic. And what they showed is that if you took the X-ray transform, but you composed it not necessarily with a smooth function, but with a smooth function that has this additional weight at the boundary of d gamma, where we take, say, gamma to be at least -1, so that everything is still integrable. If we do that, then the end result will be not necessarily a smooth function, but it will be a smooth function, in particular a C alpha infinity function, after factoring out this factor of tau to the 2 gamma plus 1. So you can think of this, for example, when gamma equals 0, we already saw an example of this where I0 of the constant function 1 is the travel time itself. Sorry, the length of the geodesic. And so,
sorry, can I clarify?
Yeah.
So it's d gamma times the set of all smooth functions, right?
That's correct.
Okay.
So this I0 d gamma. So here you can either put the parentheses as I've done here, or 1 before it. You can either think of this as the X-ray transform applied to the set of functions that are smooth times a factor of d to gamma, or equivalently, you can just start out with a function and consider the operator I0 d gamma.
Right.
Yeah. So what it shows is that if you precompose with a weight of d to the gamma, then you get out essentially a weight of tau to the 2 gamma plus 1, which means that if you divide by tau to the 2 gamma plus 1 and then compose by our back projection operator, then this certainly maps C infinity into C infinity. So this gives a choice of weights that, at the very least, satisfies the forward mapping property. And one natural question to ask afterwards is if it would satisfy the isomorphism property. In a slightly more recent paper of Matteo and Monard, it was shown that you can generalize the previous result. So the previous result had a tau, where tau is the length of the geodesic. But it was shown that, in fact, you can actually replace that by any boundary defining function for the inwards pointing sphere bundle. And so the two results are proven in slightly different techniques, but they give the same idea of results, same general idea of results. Now, those were some forward mapping properties, but in some limited cases, there are also straight up isomorphism results. So for example, it was shown in Monard-Nico patterning in 2019 that the standard normal operator, so I0 sharp I0, it maps not C infinity into C infinity, but rather d to the -1/2 C infinity bijectively to C infinity. Or equivalently, that if we were to precompose with weight d to the -1/2, then we get an isomorphism of C infinity. And the approach used there is to note that our normal operator I0 sharp I0, it's a priori we view it as an operator on just a manifold's boundary, but of course it's actually an extendable operator to a larger space. In fact, we can just take larger space to be all of Rn. So I guess in the case of the unit disk, it would be R2. But in general, this I0 sharp I0, you can view it as a operator on some extension m tilde. In this case, I0 sharp I0 is actually an extendable operator. And as an extendable operator, it satisfies a so-called transmission condition of order -1/2. This is something that was studied by Botet-de-Monvel and Hormander in the 60s. And because of this condition, then by some abstract results of regarding transmission conditions, it follows that this -1/2 carries over to this boundary defining function to tell us that a weight of d to the -1/2 is sufficient to take C infinity to C infinity. And one last result is a work by Francois himself, considering the case of the Euclidean disk, or sorry, the disk in R2 with the metric either your straight up Euclidean metric, or more generally any constant curvature metric, which still makes the disk simple. And in that case, it was shown that instead of considering a weight before I0, if we instead consider the weight tau to the -1 in between I0 and I0 sharp, then such a weighted operator is in fact an isomorphism of C infinity. So note that this is essentially a case of, let's say, I0 tau -2 gamma -1 I0 d gamma in the case gamma equals 0. So it was shown that that I0 sharp tau inverse I0 is a isomorphism of C infinity, and the proof in the Euclidean case follows by computing the singular value decomposition of I0, and then making some comments there. And for disks of constant curvature, so simple constant curvature disks, this follows by choosing an appropriate diffeomorphism between the disk of constant curvature and the Euclidean disk, and intertwining the operators to give you the results. So, the results in this work, so are going to be following a lot with the paper by Monard 2020, basically generalizing this case of just this particular weight tau to the -1 to a more general class of weights. So yeah, so in discussing when we have these isomorphism results, I should point out that in the paper by Matteo Monard earlier this year, there was a conjecture that recall on the last slide that in this paper it was shown that for any boundary defining functions that this operator I0 sharp t to the -2 gamma -1 I0 d gamma is at least maps C infinity into C infinity. And the conjecture was that by choosing D and T appropriately, so by choosing the boundary defining functions appropriately, you can actually arrange this not just to map into C infinity, but rather to map bijectively into C infinity. And so this should hold for, let's say, any simple Riemannian manifold. And what we can show is that this at least holds in the case where our manifold is just the Euclidean disk. And here we give very explicit boundary defining functions. So in the case of the Euclidean disk, we can say the following. If we consider the boundary defining function 1 minus the radius squared, and this will be, so this is the boundary defining function on M itself, and we consider the function mu on the inward pointing sphere bundle, then I0 sharp mu to the -2 gamma -1 I0 d gamma is an isomorphism of C infinity, as long as gamma is greater than -1 in order for everything to be well defined. So, this notation mu was introduced a few slides ago, and just to remind you, this mu is a function on the inward pointing sphere bundle, which, given a vector in the inward pointing sphere bundle, just takes dot product of that vector with the inward pointing normal. So this will be positive in the interior, and it will be 0 along the boundary of the inward pointing sphere bundle, which is you can think of that as the vectors that are tangent to the boundary itself. And in fact, this this dot product mu is actually very closely related to the length of geodesic in the case of our Euclidean disk. And in fact, in the case of Euclidean disk, this mu is actually just 1/2 the length of geodesic, or equivalently, the length of the geodesic is 2 meters. So this is our main result. And note that this result gives you a family of weights that give you a C infinity isomorphism, and this family of weights generalizes the two results that were listed earlier, specifically when gamma equals 0 and gamma equals -1/2. So recall from the previous slide, if we plug in gamma equals 0, we get the case of I0 sharp tau to the -1 I0, whereas if we plug in gamma is -1/2, we will get I0 sharp I0 d to the -1/2. Both of these were shown in the prior to be isomorphisms of C infinity, and in some sense, this work gives us a unifying way to generalize both of these results. Okay, so let me just briefly point out the outline of how this proof goes before diving into the details in the remaining time. So the idea here is to break up this weighted normal operator. So this a priori has 4 components, but we're going to break it up into 2 components of 2. And so the first component here is the I0 d gamma, And it turns out that it actually maps boundedly from L2 with a weighted measure. It's the Lebesgue measure, but weighted by Yuzhou gamma. And it maps boundedly into L2 of the inward pointing sphere bundle, but with a weight of mu to the -2 gamma. Furthermore, it turns out that this turns out to be the precisely correct weight, so that when we consider the adjoint of this operator defined with respect to these particular Hilbert spaces, then that the adjoint is actually just the other two parts of our weighted normal operator, namely I0 sharp mu to the -2 gamma -1. In other words, if you want to study the mapping properties of this overall weighted operator, this is actually studying the composition of I0d gamma with its adjoint, whereas the adjoint is defined with respect to these two Hilbert spaces. So phrasing things like this, we can then break down the proof into 5 steps. And I'll list the 5 steps here and maybe then take a break to see if there are any questions. So the 5 steps of the proof are the following. So first, so we've broken up our operator of interest into, I0 d gamma and its adjoint, which is I0 sharp mu to the -2 gamma -1. And we've first established intertwining relationships between this particular operator with certain differential operators, both on our physical space, the disk, and on our data space, the inward pointing sphere bundle. Secondly, once we've established intertwining relationships between these differential operators, we can then observe that those operators admit special classes, special eigenbases consisting of certain classes of orthogonal polynomials. And that allows us to compute, or really more accurately, rederive some known results about the singular value decomposition for this operator I0 d gamma. With the singular value decomposition in mind, we can, in fact, obtain an explicit formula for the singular values, and we can compute the asymptotics of the singular values. And in particular, we obtain polynomial, or I guess inverse polynomial upper and lower bounds in an appropriate sense. This then motivates constructing spaces that somewhat resemble soulless spaces, which basically depend on iterated regularity with respect to applying our differential operators obtained above. And we will construct these spaces with a property that our overall operator is well behaved with respect to these spaces that we've constructed. And finally, we show that these spaces are specified some nice properties, in particular that in analogy with the Sobolev spaces, that their intersection is the space of all smooth functions. And if we can obtain good mapping properties of this operator between each of the Sobolev spaces, then we obtain a good mapping property on their intersection, i.e. on C infinity. So this is the outline of how the proof in our paper goes. So before going further, are there any questions on any of the results or anything else I've said so far? Okay, so in the time remaining, I'll try to highlight some. So as you can see, I have several slides left, but I won't go through all of them in full detail. I'll just highlight some of the highlights of the various parts of the proof. So the first step, so here we're working explicitly on the Euclidean disk, which means we can give very explicit coordinates on what we're doing. Specifically on the Euclidean disk, we use polar coordinates, and on the inward pointing sphere bundle, we can use Van Beek coordinates. In which case, our boundary defining function d and tau become 1 minus rho squared, rho being the radius, and tau you can express in terms of the two angles here as cosine of alpha. So then we can then show that the operator I0 sharp mu to the -2 gamma -1, it will intertwine two particular operators, the T gamma and L gamma. T gamma will end up being an operator defined on functions defined on the sphere bundle, So this notation I'll explain it on the next slide. But the main point is that it takes in a function on the inward pointing sphere bundle and gives you out this a function of the same kind. And you can describe it as a particular second order differential operator with respect to this vector field T, which is partial beta minus partial alpha. And so the formula is given here. So our operator here intertwines T gamma on the inward pointing sphere bundle side with an operator L gamma, which acts on the disk itself. So you can write it in one of two ways. And the first way here is kind of an easy way to check that it's self-adjoint with respect to our measures of interest. But we can also expand it to get this part to get that this is a particular second order differential operator. So again, the first step is just to establish that this intertwining relationship holds. And this is more or less a calculation. I will just point out that the case gamma equals 0 was originally considered in the paper by Monard 2020. And so the full calculations for the case gamma equals 0 are given there. And this still continues to hold for gamma not equal to 0 just by writing T gamma and L gamma in terms of T0 and L0 and using the calculation in the paper in 2020. So this is the desired intertwining relationship. And just a few remarks on these two operators. So first, the domain that I've taken for the operator T gamma is a weighted version of what appears to be a C infinity space. And so, if we ignore the weight, then the C infinity space is basically C infinity, except satisfying some additional conditions on, satisfying some additional conditions on with respect to scattering relations. So, for example, so in particular here, we actually start out with functions which are in C alpha infinity, where C alpha infinity is a space that was considered by Pesov and Ullmann, which mapped into C infinities via I0 sharp. So we start out with such a function. In other words, it is smooth when you extend it to the entire partial SM via the scattering relation. And we impose an additional symmetry condition, which is that it is even with respect to the so-called antipodal scattering relation. So the antipodal scattering relation is kind of similar to the scattering relation, except you flip the orientation of the vector at the very end to give you a map from the inward pointing sphere bundle to the inward pointing sphere bundle. And so we want to consider functions which are actually even with respect to that. It turns out that the collection of such functions, after weighting it by this mu to the 2 gamma plus 1, it turns out to be dense in L2, or specifically L2 plus, which is the collection of L2 functions, which are even with respect to this antipodal scattering relation. So the reason why we want to consider this is that the back projection operator itself turns out to be even with respect to this antipodal scattering relation, which means that it suffices to consider the back projection applied to functions which are even with respect to the antipodal scattering relation, since if you take the odd part of it, it just completely vanishes under the back projection. So this is kind of a bit of a technical note. I think what's more interesting is that this second order operator applied on the spatial side, this is a degenerately elliptic operator. So this is an operator which will be elliptic in the interior, but near the boundary, the ellipticity degenerates in that the coefficient of partial rho squared will vanish simply. And finally, both of these operators are in fact essentially self-adjoint when equipped with the domains that I gave. For the case of L gamma, this seems surprising at first, since a lot of times with second order operators, you need to impose boundary conditions in order to get symmetry. In this case, the vanishing of this coefficient out in front actually guarantees that you have symmetry without considering further boundary conditions. Although this is a slightly misleading statement because the domain we're working with is C infinity, in other words, continuous up to the boundary, and that itself is already a benefit boundary condition. But in any case, these operators are symmetric and essentially self-adjoint with the right domains. And what that means is if we establish this intertwining relation, then we can take adjoints of this equation and obtain an intertwining relation for the adjoint of I0 sharp mu to the -2 gamma -1, i.e. for I0 d gamma. And thus we get an intertwining relationship on I0 d gamma. We can also verify that these operators will intertwine the partial derivatives partial beta and partial omega. And thus for the overall normal operator, we obtain commuting relations of it commuting with L gamma and with partial omega. So that's I guess the end of step 1. For step 2, since these two operators intertwine the operators L gamma and T gamma, and then I guess also partial omega, partial beta, it means that they actually must also map the joint eigenspaces of L gamma partial omega and T gamma partial beta to each other. And that means we want to consider joint eigenfunctions of the above pair of differential operators. It turns out that both pairs have simple joint spectra, which means that for each operator, maybe the operator itself will have multiplicity for its eigenvalues, but if we consider the pair of these operators, then each pair of eigenvalues is simple. And due to the intertwining relationship, this must mean that each of these operators must map a joint eigenfunction of one of these pairs to a multiple of the joint eigenfunction of the other. So this motivates studying the joint eigenfunctions of these pairs. So for example, for T gamma and partial beta on the data side, an explicit eigenbasis, joint eigenbasis for these two operators is given by this formula, which is mu to the 2 gamma plus 1, which is our weight, times this exponentially varying complex exponential, but with a input of beta plus alpha, times a particular orthogonal polynomial applied to sine alpha. This particular orthogonal polynomial is in fact related to the ultraspherical or Gegenbauer polynomials. And if we then proceed to consider what is the image of I0 sharp mu to the -2 gamma -1 on these sine k gammas and call these z and k gammas, then it turns out that either it just gives you identically 0, which happens for several cases, namely if k is not between 0 and n, or it gives you a non-zero polynomial whose leading order coefficients you can actually explicitly compute with respect to the leading order coefficient of the L and gammas defined on the previous slide. And furthermore, we see that these D and K gammas will then give us an orthogonal basis in L2 of the disk with a weight b to the gamma, basically via the intertwining relationship here. Once we have this, then I guess in this time I'll just skip ahead a little bit. Once we have the intertwining relationships, then this allows us to compute the singular value decomposition of I0 d gamma, which, to be fair, was so this actually rederives the singular value decomposition originally obtained in a paper by Lewis in 1984, where he computed the SVD of radon transforms, which in 2 dimensions is the same as the X-ray transform. And so these special classes of polynomials gives us the SVD of I0 d gamma, and furthermore, the output z and k gamma here, these polynomials are not just any mystery polynomials, but they're actually part of a family of orthogonal polynomials that have been studied, for example, in a paper by Wunsch in 2005, and these are the so-called generalized Zernicke polynomials. So if you have experience in orthogonal polynomials, is given by this explicit formula. But the point is that we can safely conclude that I0 sharp I0 sharp mu to the -2 gamma -1 takes our sine k gammas to multiples of these Zernicke polynomials. This is beneficial because we can express the singular values of the SVD as a ratio of the L2 norms of these polynomials, and this ratio can then be computed by tabulating results of orthogonal polynomials, for example, in Wunsch's paper or in Sego's classical book on orthogonal polynomials, etc. So step 3, we can obtain an explicit formula for these singular values, and we can then try to ask, so this depends on n and k, and we can ask, well, how does these asymptotes look in n? And essentially, by an explicit computation, some explicit asymptotic analysis, we can conclude that the singular values decay at an inverse polynomial rate. So unless gamma equals 0, the upper and lower bounds that we obtained are not sharp compared to each other, but nonetheless, both of them give inverse polynomial upper and lower bounds, which is what turns out to be important. In the case gamma equals 0, which was originally studied in 2020, in Monard 2020, the expression actually, in fact, simplifies greatly to not depend on k. But in general, we can still at least make this non-sharp asymptotic statement, from which we can then say, well, this motivates considering Sobolev type spaces that are defined with respect to these Zernike polynomials, since the Zernike polynomials form the SVD for our operators of interest. And so what you can do is you can basically define this H as gamma tilde kind of analogously to how you define Sobolev spaces, except this will be defined, if you want to think of Sobolev spaces as defined with respect to powers of the Laplacian, this will be defined as with respect to powers of our operator L gamma, which is similar to the Laplacian, except that it's degenerately elliptic at the boundary. So you can do some nice analysis here. And the main result is that based on the asymptotic bounds on the singular values and our definition of our Sobolev spaces, we get some, not the sharpest, but still some decently sharp mapping properties on how our operator of interest acts against these Sobolev type spaces. So at the very least, we get this chain of conclusions. And finally, these Sobolev spaces, Sobolev type spaces are actually very nice in that they intersect to C infinity. And this itself uses some more results on our orthogonal polynomials. So in particular, it involves getting an L infinity bound on Zernike polynomials, which is equivalent to really looking at the L2 norms of the Zernike polynomials, since we're normalizing it here, as well as looking at the relationships between Zernike polynomials and differentiation. So, so actually, there's a bit of a typo here. Something interesting here is that the differentiation takes these Sobolev spaces, which which a priori refer to this parameter gamma, and actually increases the gamma parameter by 1. So here, these actually should be +1s. But in any case, the point is that you can make these kind of statements, and this gives us at the intersection of our Sobolev spaces is to infinity, which combined with our, not completely sharp, but still good mapping properties on the Sobolev spaces, gives us that it takes C infinity into C infinity, and in fact, it gives both inclusions by taking intersections. And thus, that shows that this particular operator is a bijection on C infinity. So this is basically what we did in our paper, and so I'm not sure if I'm supposed to go into 10, but if so, I have about 2 minutes, and I'll just mention some other parts of this work. So in addition to C infinity isomorphism, the above work also gives a stability estimate that I alluded to as one of our motivating factors. And here, the stability estimate is with respect to these Sobolev type spaces that we defined. And so now this on its own, though, it is it is a nice estimate, but it still requires a bit more work to fully understand what this means, since we would need a slightly better understanding of how these Sobolev spaces work. So for example, these Sobolev spaces, if something is in these HS gamma tilde, then they need to be HS in the interior, because you can view this as being defined by L gamma, which is elliptic in the interior, but the boundary behavior can be more degenerate than boundary behavior of HS functions. So a bit more work will need to be done to study what these Sobolev type spaces actually are, but at the very least, you can get to this kind of bound. Secondly, since we considered these explicit polynomials on the data side, we can, and we saw that in fact the adjoint, the projection took a lot of these to 0. We can in fact characterize the kernel of the adjoint and thus give a range characterization of I0 d gamma itself. And range characterizations for the X-ray transforms are something that is also very important, kind of related to the situations where you want a isomorphism result. And finally, everything here was discussed in the case of the Euclidean disk, because you can do very explicit computations there, but you can also extend this result to simple geodesic disks of constant curvature. And the short way to say this is that there's a way to choose a particular diffeomorphism between a disk of maybe non-zero curvature to the Euclidean disk, such that intertwining this diffeomorphism with our Euclidean operator gives us an operator of the desired form. So let me just finish off by saying some future directions that we're working on. So first, this work involved studying eigenfunctions of this like Chimera type degenerate elliptic operator L gamma, specifically eigenfunctions on C infinity. But it turns out that this operator actually will emit more self-adjoint extensions, say if it were initially defined on C infinity. For example, if you consider C infinity, but with this additional weight of d to the minus gamma, or for the case gamma equals 0, this weight of log d, then it turns out L gamma is actually also essentially well-defined and essentially self-adjoint on this space. And for gamma between -1 and 1, this gives a genuinely different self-adjoint extension than the closure of C infinity. And studying these different self-adjoint extensions could help explain the binding properties of our desired operator on more function spaces than just C infinity. Furthermore, more work can be done in studying these Sobolev spaces, and of particular interest is this case gamma equals -1/2, since the case of gamma equals -1/2 was originally proven using the transmission spaces studied by Hormander and Grubb and etc. And at this moment, it's not clear that it seems that these two approaches are completely orthogonal to each other, and it would be good to ask how these Sobolev type spaces relate to the transmission spaces. And finally, everything here was done very explicitly for the case of the Euclidean disk, but we would like to extend the C infinity isomorphism result to more general surfaces with boundary. And one possible approach we could do there would involve using the zero calculus developed by Mateo and Melrose to study some problems on manifolds with boundary. Okay, so that is my talk, and thank you all for your attention.
Thank you very much, Joey, for the very, very nice talk. Are there any questions or comments, please? Any questions or comments, please? Okay, if not, thank you very much. Oh, please.
So, can you hear me?
Yeah, hi, Jan.
Perfect. Hello. Very nice talk. Thank you very much, Joey.
Thank you.
So I've got a question about the choice of gamma. So I think the ones that have appeared in the literature so far are -1/2 and 0, right?
Yes. So those are the ones where there have been previous isomorphism results.
And so, I mean, they seem, or they crop up quite natural because you get like particular measures on the influx boundary. Is there a motivation for the other values of gamma?
So I don't have a direct answer other than, I mean, why not? But I think, but at the very least, to me, it seems useful to have gamma ranging, to have a result for gamma ranging continuously. So we get so the result that we have is for all gamma greater than -1. And so it seems, at least it seems to me, that if you are able to get a get this isomorphism result for a continuous range of gamma, then that might be helpful in future results if you need to use some kind of interpolation or something.
Does interpolation already play a role here between different gamma values in some way?
In some sense, yeah. So in fact, specifically, yeah, I guess interpolation plays, for example, a role in establishing the C-infinity isomorphism. Sorry, the C-infinity intersection property, just because. So I don't know if this is really interpolation, but at the very least, the result we used was that these, a result on the Zernike polynomials, its behavior under derivatives, but shifting up the parameter by 1, and thus requiring us, even if we started out with some gamma to start considering, we needed to get results for higher gammas as well. So in some sense, there is some interpolation going on here. I guess like if you could also say that the Sobolev spaces themselves are defined by interpolation, based on powers of the L gamma. Yeah, but other than that, I'm not so sure.
Okay, thanks.
Yeah, no problem. Yeah, Francois.
If I can add to this, thanks, Jan, for the question. It's also in trying to understand these mapping properties, in exploring all possible toolboxes that are available. This continuous family of cases with gamma is something that's coming from the SVD that was already known. And so then, when I saw this, I was wondering whether we could exploit all the properties that we could do to get these mapping properties. Yeah.
Thank you very much. Are there any other questions or comments, please?
Can I ask something?
Please.
Hey, Joy, good talk. So do you have anything about mapping properties of just I, like with a weight, like, I don't know, raising your your Sobolev rate by half or something like that? Is that
so are you saying I0D gamma?
Yeah, like with a special choice of weight, or I don't know.
So I guess like the one mapping property about I0D gamma itself mentioned here is the mapping is a range characterization of I0D gamma, which just I guess follows by considering explicitly noting that we can find the kernel of the adjoint. In terms of like but I guess you're asking about can we get Sobolev regularity on I0D gamma F in terms of F, Sobolev regularity on F, or vice versa. And that's, to my knowledge, maybe Francois can correct me, but I don't think that's something we've considered yet. Mostly because like this would involve considering measuring regularity on the partial plus SM. And I mean, of course, we can just use the standard Sobolev spaces there. Those are well defined, but it's not clear right now exactly how they interact, just because our special Sobolev spaces are, a little bit. It has some interesting behavior on its own. But I guess as far as I can tell, I guess as far as I can tell, we don't have such results yet.
Thank you.
Yeah, it's a case where we know everything about it in terms of special functions, and then we have a basis of vector fields. We know exactly what they do to the eigenfunctions, and so then you could start thinking about how could you cook up Sobolev type spaces So then you ask yourself, what's a Sobolev space in the first place? Are you trying to define this in terms of L2 derivatives with respect to some vector fields? And then, and so if that's the case, you stare at the vector fields you have, they form a basis, and then you realize that that this range of action might actually not even be good enough to formulate sharp mapping properties. So that's one of the funny upshot of the, outcomes of this work in some sense.
And so you wouldn't be falling into the same space, which is probably a bad thing if you're trying to look at I0D itself, right?
Well, the short answer is you have the Seeger value decomposition, so you can define ad hoc spaces spectrally in terms of spectral decay. You know exactly that you have on the image, on the range space, you have some type of decay with these with spectral values that have this specific decay. Then there's kind of two directions on the lattice of frequencies, and then you stare at on this lattice of frequencies what the basis of vector fields do, and then there is no way of really capturing this using using just it's just it's too complex to capture with just vector fields. You could write some kind of like funny function of two variables of those two vector fields or something, but then at that point it's like quantize, some kind of like non-polynomial quantization of vector fields or something, and then define your Sobolev spaces based on that. So then at that point, okay, it's just a ad hoc construction. Is it worth writing?
Yeah.
Yeah, so I guess I will point out that so in part of what we were doing, at least for the Sobolev spaces on the physical side, that what is it here? So okay, so I guess I don't have this doesn't give us all of the properties, but so for each HS gamma, so it contains it properly contains HS, but at least let's see if that's an integer. But it is also contained in some in some standard Sobolev space of rather significantly higher order. So if you want to express everything in terms of the standard Sobolev spaces, for example, you should be able to translate our results into such estimates. However, there is almost no chance that it will be a sharp estimate.
Thank you very much. Thank you very much. Are there any other questions or comments, please? If not, thank you very much, Joy, for the very, very nice talk. Thank you very much, everyone, for coming. Thank you very much.
Thank you all for